All right. Hello again, and hello for everyone who is watching. So today we're going to move a step backwards from linkages. You remember last lecture, what we studied was serial linkages. And by that, I mean, we studied how to find forward kinematics equations for serial linkages. And as you said last time, I think it is kind of trivial, right? It repeats what you did in theoretical mechanics. In many ways, it is just find the position of a point of a pendulum knowing joint angles. Simple. All right. While this is simple, next lecture, we're going to go to spatial robots. So spatial robots would have kind of same idea, except we would have to deal with what we call frame transformations. We would have to deal with the fact that some of our links work in, how should I put it, expressed in frames which are themselves defined in terms of other frames and so on. This just leads to confusion. The material itself is at the core as simple as the previous lecture. That is my view. Maybe I'm wrong. But the idea of forward kinematics for in space is, can be at its core as simple as kinematics in 2D. And I say that because, for example, when I write software for 2D robots, instead of writing it for 2D specifically, I just use a special case on 3D. And the equations themselves, except for angular velocity, are trivial. There is almost no additional overhead in terms of thinking or in terms of code that you have to do for forward kinematics once you know what you're doing. All right, so at the core, spatial forward kinematics is simple, but conceptually it is difficult. And what I'm trying to kind of convey to you is that what we have to overcome in this lecture and next lecture is conceptual difficulties. So we need to understand what's going on. It's not like we have to acquire a very difficult tool set. Instead, we have to acquire a concept. And then the tool set itself is like a couple formulas, which are very easy to use. Okay. And in practice, most people, the formulas that are very simple, they just memorize because they're like a couple lines. More difficult formulas, people use cheat sheets, so it's fine. But the conceptual understanding is what what is between you and successful use of forward kinematics. With that in mind, I'm going to risk dedicating a whole lecture specifically to linear transformations from the algebraic point of view. This is a risk, and this is a risk because, in a sense, you can say this lecture could be spent on directly addressing forward kinematics of robots. Instead, we are going to address linear algebra of transformations. We have time in the course for that, so that is not a problem. But we could say it is a risk. Another risk is that you will be bored and stop listening to me midway through. So I will try to pace myself. But anyway, my hope is with this lecture, I will try to somehow give the concepts that you will need. Let's be more concrete. All right. So I think the most difficult part of frame transformations is the understanding change of bases. Okay. Frame transformations, I will give you overhead view and we'll go, then step by step. Frame transformations is, you can imagine a frame as 3 vectors. I'm trying to use my fingers as 3 vectors, orthogonal to each other, like one vector, another vector, another vector. right? They are orthogonal to each other, frame transformation. So a frame, sorry, attached to a point. So 3 vectors attached to a point is a frame. So when we call frame transformation, talk about frame transformations, we, for example, can talk how to translate a frame and rotate a frame. Or we can say, we have 2 frames. What is the distance between them in terms of translation and rotation? That is what we are talking about. So you can imagine attach a frame to ground, attach a frame to the end effector of a robot, to the gripper of KUKA, for example. And what is the translation and rotation between those 2? Those are frame transformations. Translation part, I think, once you understand change of basis, is not very difficult. Maybe I'm wrong, but we can cover it too. Is in like details is easy. Change of basis, however, I think can cause problems, and not because it is difficult, but because it somehow requires different thinking. Okay, so with that in mind, what I propose is slightly different approach to what we usually see in modern robotics textbooks. So again, there is a risk in my approach. I'm going to teach you like slightly different way compared to what a typical textbook will teach you. Plus side, you can still read the textbook. You would get information from there, but you can also get my explanation. Maybe it will work for you. For me, it worked very well. So we'll see. So the idea is, I will try to teach you to think about linear transformations or change of basis in terms of abstract vectors instead of coordinates. Okay, so this is going to be a little bit that's going to be a little bit difficult to like in the start, but we'll see hopefully what I mean. We're going to talk about abstract vectors instead of coordinates. So here's the motivation. I will just give you like an idea. The motivation is this. If you want to perform transformations, thinking about vectors in terms of coordinates, there are 3 things you have to think about. 3, right? One thing is vector, right? The vector which you're going to work with. Another one is coordinates, so the basis in which it is expressed, because coordinates mean you are expressed in terms of some basis. And last is the transformation. So 3 things: vector itself, basis in which it is expressed to give you coordinates, and transformation. Okay. You can think that maybe I'm exaggerating, but I'm not. For example, if you look at if you look at notations that we use in robotics, we usually have for forward kinematics upper scripts. Upper scripts, you understand what upper script is, right? Is something on top of the variable. Superscript, subscript, I don't know. Upper script. So anyway, this thing refers to the frame in which the vector is expressed. All right. For linear transformations, we usually also like for the matrices, basically, we also have those upper scripts. So here, like instantly, you have 3 entities: the frame from which it transforms, to which it transforms, and in which coordinates it is expressed. Yeah, so it's difficult. Juggling those things in mind. In abstract vectors, you won't need to think about the basis in which it is expressed, and that would make your life simpler. All right. Let's dive in and see if this somehow helps and clarifies. All right. First, a little bit of pure linear algebra. Please bear with me. and try to like pay attention. I understand this is like, you know, flashbacks to your first grade, but it's good. Let's try. All right. So consider vector A in L. L is a linear space. Let me try to mark it. So L is a linear space. Usually we think about linear vectors as living in space Rn, right? Usually we think about vectors as living in space Rn. So basically we think about vectors as a column of numbers like 2, 3, 4, 5, etc. That is not the, like all vectors that you can imagine. That is just one specific vector space. You can also think about vectors as arrows, right? Like what I draw here. This is an arrow. So you can think about vectors in this way. Those are also vectors, and they, you know, they don't have to be expressed as a column of numbers, right? Can just be arrows. Those arrows have to have a common origin for it to be a linear space, kind of like what I'm drawing here. Those arrows form some sort of a vector space. Okay, sounds good. Can someone give me another examples of linear spaces other than arrows? There's one in the chat. Linear space is any space where linearity property holds. Am I right? Yes. I don't like to give like answers about definition of linear space without being prepared, because maybe I'm forgetting something. But yeah, in general, you can think about it this way: space where linearity holds. Also, yeah.
Sorry, Professor. I just want to tell some example of linear space.
Yeah, please.
For example, rational number on sorry, not rational, real number on rational numbers.
A linear space?
Yeah.
Rational numbers on real?
Oh, sorry. It's not linear space. I missed with vector space.
Vector space. Yeah, no, vector space, linear space. Vector spaces and linear spaces are synonyms.
So if they are synonyms, I believe that rational numbers on field of, real numbers on a field of rational numbers is a linear space.
No, I think you're trying to go somewhere like in a different direction. Like numbers as in scalars, of course, always would form a linear space if you treat them as vectors, as linear elements, right? If you say, okay, do they have properties of distributive property or stuff like this, right? Do they behave like linear objects? Of course they do. But sorry, the noise will go away in a second. You are thinking right now more about theory of fields, rings, etc., group theory. I'm thinking about linear spaces specifically. So can someone give me more examples of linear spaces? Matrices. Yes, matrices are linear, former linear space. Yes. But matrices, again, is just tables of numbers. Can someone give me an example of a linear space which is not a table or a column of numbers? I mean, I don't know if you studied this, so I'll just wait for a minute, then I'll give a few examples.
Did you mention the directed lines and real numbers?
So any numbers, again, of course, form a linear space.
No. Directed lines aka vectors and on the real numbers.
Directed lines, as in what I draw on the slide. Yeah. Yep. That's one example. All right, let me give like a few examples. One is, I mean, I would don't give like too many, but just a couple. One is polynomials. Polynomials form a linear space somehow. If you remember Fourier transformation, or like approximating functions with signs with different frequencies, those form a linear space. Those things like polynomials and trigonometric functions, they don't have, like you can see that they are not even close to being similar to columns of numbers, right? For one thing, trigonometric functions, which you use in Fourier decomposition, form infinitely dimensional linear space. There's like if you decompose the typical function, which is not periodic, you would have infinite number of Fourier coefficients, but therefore they form a linear space. Yep. So I guess what I want to say is there is absolutely no reason to think about linear spaces as columns of numbers only. Some of the objects that behave like linear, like vectors, are not vectors at all. But there is equivalence. There is equivalence. So all linear spaces can be connected to each other in a certain way, which I will show you in a few slides. All right. Now let me just go on a little bit. So for this lecture, we will try to think about vectors as like arrows. So please don't think about them as columns of numbers. That is the thing. All right. When I say A here, please don't think about it as a column of numbers. It's not like you cannot tell me that A is like 1, 3, 0, or something like this. No, it's just arrow. Just point somewhere. That's it. It has direction and length. That's what A has. Okay, good. All right. Now let's consider n such vectors: v1, v2, v3, vn. They're all elements of linear space L. So let's say A is in the span of those vectors. Do you remember what span is?
Set of linear combinations.
Yeah, that is the set of all linear combinations of those vectors. So let's say A is a vector that can be achieved as a linear combination of v1, v2, vn. So what it means, if you remember the definition of a linear combination, is that we can find such coefficients alpha 1, alpha 2, alpha n, which are scalars. Notice this is the first time when we encounter real numbers here, because those are scalars. Again, I apologize for the noise. Those scalars that allow us to express A in terms of vectors vi. So we have A equals to alpha 1, v1, alpha 2, v2, plus etc. alpha n, vn. So A is a linear combination of those vectors. Does it make sense? Like what I wrote here, that is just the same as what I wrote here. I say if A is a linear combination of v1, v2, vn, that means A is in the span of v1, v2, vn, right? And this is written as A equals to coefficient times v1 plus coefficient times v2, etc. Right? So for now, we didn't do any math. I just said that consider that such A would have this structure. But notice for the first time, again, I stressed, we have real numbers here. Like those don't need to be expressed in real numbers. They can be arrows. They don't have any numbers behind them at all. Real numbers appear only.
Excuse me?
Yes.
So you said that we should abstract like vectors from our like yes. Usual perspective as columns of numbers, yes, to just some abstract. Yes. But how we should like imagine or describe scaling?
Addition.
Of, not only addition but also scaling.
Okay, let me show you. So those are v1, v2. I drew them just now. I'm going to scale them by 2 and add them up. So first I scale them by 2. And then I add them up. And the result is this vector. Oh, let me undo this. The result is this vector. So the red one is A. Green vector, so pink vectors, small ones at the beginning, are v1, v2. Green ones are alpha 1 v1 and alpha 2 v2. And the red one is the addition of them using the geometric rules. You remember how in geometry we add vectors. Like the sum of two vectors is the diagonal of a parallelogram.
Yeah, it's understandable. I mean, yep. If even in this example, we can express this. We can show this example using vectors as columns of numbers.
Yes, but, yes, exactly. Great. That's a great question. So what I was trying to tell you is to think about vectors in terms of arrows. But I did not tell you to imagine that it is impossible to think about them in terms of coordinates. Every vector, no matter what you come up with, can always be represented in terms of coordinates. Always. That is always true. There is a theorem in linear algebra that says that every linear space is similar. I'm using the word, I don't remember what the correct terminology is, similar to Rn. So there's always, you can always find a equivalence between Rn and any other linear space. So always true. But I'm asking you to think about errors, not in terms of, not numbers, right? You can put coordinates here, please don't. That's what I'm asking you. Okay, you got me?
Okay, thank you. Yep.
No, it was a very, very good question. I'm glad you asked. Okay. Now I think it is clear what we done here. We just found A as a combination of V1, V2, etc. Good. Now we defined a. So we can define linear operations that map L, this vector L. Oh, sorry, this vector space L to itself. So for example, let M be such operation. So M maps L onto itself. When I say L is mapped onto itself, what I mean is so the result of operation lies in the same vector space. So if we have a vector like this, the result of the operation will be another vector, but it will be in the same vector space. So it'll be there. It won't exist in a different dimensional space. It won't become a different type of entity. It would just be a different vector. All right. I apologize for the audio today. Next time we'll try to do something about it. All right. Now, M is a linear operator. So what it means is there is a property of linearity here. So M of a linear combination is the same as a linear combination of M. So let me show it again. M of a linear combination here is a linear combination of M's. So see, here we perform an operation on a weighted sum of two vectors. But it is the same as performing the linear operation on the first vector, on the second vector, and taking their weighted sum. Expression 2 is clear, right? Someone tell me, is expression 2 clear? Okay, Ivan says it is clear. Expression 2 should be like a core thing that you study in linear algebra. So should be hopefully clear. All right. So notice that those are scalar coefficients again. So those are real numbers. Okay. Now, this is useful because now for our vector A, which you remember is alpha 1 v1 plus alpha 2 v2, etc., we can use this operator to perform operation on it, and it will turn out this way. So it will turn out like this. So the operation on the A becomes an operation on v1, v2, vn, scaled by alpha 1, alpha 2, alpha n. You got my idea? So instead of performing linear operation on the vector A, which I don't know how you would do it, somehow, instead we perform it on v1, v2, v3, vn. We don't necessarily know how this is done either, but the good thing is there are only n vectors. Let's say there are 3, like v1, v2, v3. We only need to know 3 answers, right? If we defined M, we only need to define what it does on v1, on v2, on v3, and then we know everything about what M does for any A. Because we can always just scale the result and sum it up. You understand? Let me show it a little bit. So imagine you have 2 vectors, v1, v2, and you know that there is a vector A, maybe this vector A, maybe there is this vector A, maybe there is this vector A, maybe there is this vector A. There is infinite number of vectors A. You have no idea how to define M on this vector space. Like it just looks a little bit crazy. How do you define what M does on this vector space? But let's say you just say, okay, my M operation turns those 2 vectors, initial 2 vectors, into those green vectors. So rotates and scales them. Let's say that is what it does. Then you know how it acts on all those purple vectors, right? Because if you know what it does on pink vectors, those violet vectors, they are just linear combinations of those pink vectors. So you automatically know how they are transformed. You get my idea? So just you just define what it does on 2 vectors, this linear operation, and you automatically defined what it does on every vector that is defined in terms of them. That is what is important. Right now, this sounds maybe a little bit far removed from practice, but this is a key moment. So let's try to make sure we understand what's going on. Right now, I defined a linear operation M without actually talking about numbers. I didn't say multiply by a number. I didn't say rotate. I didn't say anything. I mean, like on this picture, I just said, okay, this vector goes here. This vector goes here. That's it. And this is a legitly linear operator because you can then, if you know how to express those other vectors in terms of pink vectors, you will know what happens with them under this linear operation. So without numbers, without using matrices, we define the linear operator. And it is a legitimate linear operator, M, that operates not on numbers, not on columns of numbers, just on something, on arrows. Please let me know if this makes sense. Okay, good. Thank you, Ivan. Okay. Okay. I mean, anyone who feels like this doesn't make sense, please ask. I will try to explain in a different way. So, all right, we'll move on. Now, as I said, it is useful because like this thing that we just did is useful because we, instead of defining M for any possible A, we only define it on V1, V2, Vn. Okay. Oh, great. Anastasia says that this looks very similar to what Professor Shilov gave you on differential equations. That is what I was hoping. I'm hoping that what I'm teaching you here will remind you of what you already had in linear algebra equations. Okay. Okay, good. So anyway, and now let us define what M does on those vectors this way. So remember the picture that I drew previously. Let me draw something like this again. So we have two pink vectors, and they are transformed into green vectors. This way, okay? So those pink vectors are transformed into green vectors. Okay, okay. Now I will just label those vectors as the first transformed vector will be called U1. The second transformed vector will call it U2. The last one UN. Okay. 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 So the first vector is similar to V1 is similar to U1. Sorry, not similar. Is transformed to U1. The V2 is transformed to U2. Vn is transformed to Un. Okay. Okay. All right. Now, here we start to use a little bit more assumptions. If V1, V2, Vn form a basis in L, basis means it spans L, and it is a minimal number of vectors that spans L. So you can say that L is n-dimensional, and V1, V2, Vn spans L. That is one way to put it. Another one is V1, V2, Vn are linear independent vectors, and they span L, right? So if those vectors form a basis in L, then vectors U1, U2, U3, Un also can also be represented as linear combinations of v1, v2, vn. I think here we arrive at another one of those slightly conceptually scary points, but not very difficult. Let's think about it. So v1, v2, vn, they span the whole space, right? L. And u1, u2, un also are in L, because M is an operation that takes a vector in L, gives back to L. It doesn't shove it into a different linear space. The vectors are still inside the same linear space. All right. So those vectors that you get, u1, un, can of course be represented in terms of v1, vn, because v1, vn are bases. Okay. Now let us, describe this way. We say that u1 is equal to m11 v1, m21 v2, mn1 vn, right? And the same for all others. So they're linear combinations. So we just introduce coordinates v11, m11, m21, mn1, etc. Okay. So what we did here is that we expressed all vectors u1, u2, un in terms of how they, what you need to multiply v1, v2, vn by, and add them up to get those vectors. Okay. Questions? All right. Let's move a step forward. Now, when we transform A, as was the question. Yes, Ivan. We'll wait. Type your question. I'll answer. All right. So. Ivan asks, does what I just said imply that any linear operation can be represented by a matrix? Yes, it does. That what last slide, in a sense, proved that any linear operation can be represented by a matrix. Indeed. That is entire, like before I said that any vector has the equivalence with coordinates table, right? Any vector space can be is equivalent to Rn. In the same way, any linear operation is equivalent to a matrix. For any linear operation, you can find the equivalent matrix. And matrices are also linear spaces. So what you find is that there is equivalence between linear operators and linear spaces. But that is the kind of algebra which is very fun to read, but not something that I have can teach on introduction to robotics. So, but yeah, indeed, you got exactly the right idea. Okay, good, good, good. So we want to transform A using operator M. And we define that the resulting vector as B. We just call it B. We say you apply M to this vector A, what you get is B. Okay. And since V1, V2, Vn is still a basis, right? Like it always was a basis. It is still a basis. Good. We can represent B as a linear combination of those vectors. So we can represent B as a linear combination of V1, V2, Vn. It will be like beta 1 V1 plus beta 2 V2 plus blah blah plus beta n Vn. And yep. So now is the question. What is the relations between beta 1, etc., beta n, and alpha 1, etc., alpha n? What is the relation between the two? I don't know if this question makes sense, but what I'm asking is, in terms of coordinates in this basis, what is the relations between the output of the separator and the input of the separator? So we have transformed vector B represented by its coordinates in this basis. And we have original vector A represented by coordinates in this basis. What is the relations between the two? We have a very good guess from Anton in the chat, but not precise, but yeah, Anton is on the right track. All right, let me show you. What I'm going to show you now looks scary, but you don't need to think about it too much. It is not like hugely important. This is more for to illustrate. You don't need to memorize any of this, so don't worry. Now, what we do is this. We say M, we want to apply M to A. We already know that this is true, right? This is the same as linear combination of M of V1 plus M of V2, M of V3, etc., multiplied by alphas. Now we know what this is. We know that, let me show you. This is that. We know that this is that. So we know that operator M applied to V1 is a U1, right? U1. And we know that U1 is M11 V1, M21 V2, etc. Right? We know, so we can represent it this way. And opening the brackets, what we get is something like this. We have coefficients in front of V1, coefficients in front of V2, coefficients in front of Vn. And those coefficients, but it is, as we said before, this is B, and B is beta 1 equal times V1 plus beta 2 V2, etc. So that means that these coefficients have to be equal to beta 1. This sum, oops, let me do it this way. This sum has to be equal to beta n, right? And all in between. So you have to have equivalence between what stands in front of V1, V2, Vn. I'm not proving this, but you can prove it. The way you prove it has to do with the fact that V1, V2, Vn are linearly independent. And they are linearly independent because they are bases. Right. Now, what you have now is expression of how beta 1 corresponds to alpha 1 alpha 2, alpha n. So you can express betas in terms of alphas. Notice that this expression that I boxed is only in the real numbers. Now we don't have any vectors there at all. Those are just scalars. All of those are scalars. Just scalars. Okay. Okay. Now, next. This expression can be represented equivalently as a matrix vector multiplication. And now you can see what's going on, right? Those coefficients that represented basis transformations, so how U1, U2, UN looks in terms of basis. Let me remind you what it is. Here where we got them from. We said U1 is a combination of U1 looks this way after transformation. U2 looks this way after transformation, etc. So that is where the coefficients come from. How the basis is transformed by M. And indeed, how basis is transformed by M is exactly this matrix that would represent this linear transformation. But notice, please, that this matrix transforms coordinates of A before transformation into coordinates of A after transformation. One second. Yep. So, what we have is relations between coordinates expressed by matrix. It's not relations between vectors, it's relations between coordinates. What I hope this kind of drove home for you is that vector matrix multiplications explain how coordinates transform. But the original operations, like the original operation here, M, had nothing to do with it. M could exist without those coordinates. It's just just linear operation. And if we didn't have this basis V1, V2, Vn, we couldn't get those coordinates at all. So coordinates came because we have V1, V2, Vn. So this whole thing depends on the basis. This is the coordinates of the original vector in the basis, of the resulting vector in the basis, and this is a representation of the operator in the basis. I think now maybe you start to grasp what basis actually means, right? It means everything when you talk about coordinates. If you want to do vector multiplication, vector matrix multiplication, you have to make sure that you're, or if what I'm trying to say, if you want to use vector matrix multiplication to express a linear operator that acts on a vector, you have to make sure that the linear operator is expressed in the same basis as the vector itself. And the result would also be expressed in the same basis. And the result would be coordinates, not the vector. Okay, I think we got the idea. I think we got the idea. Ask me questions if something is not clear. I would be happy to qualify. All right, let's we'll just look at it, and then just a little bit more algebra, and then we'll go into mechanics. Okay, so what we learned is vectors and operators exist separate from the coordinate representation. When I say separate, you don't. What I'm trying to say is you don't have to think about coordinates. you can think directly about vectors and operators. Second, coordinates are associated with bases. So you want coordinates, you have to have a basis. And coordinates describe both vectors and operators. Okay, good. Now, more complicated example. Let's say you have one basis, V1, V2, Vn. And you have a second basis, omega 1, omega 2, omega n. If we know coordinates of vector A inside the first basis, can we find its coordinates inside the second basis? That sounds maybe, I don't know, a little bit closer to what we actually are expected to do in robotics, right? We know A in the first basis. We want to find A in another basis. Okay, okay. So let's say that A in second basis has this representation. So it is gamma 1 V1, gamma 2 V2, omega 2, gamma n, omega n. Now, what we want is to find gamma 1, gamma 2, gamma n in terms of coordinates of A in V1, V2, Vn. So alphas. All right, all right. So first we want to represent omega 1, omega 2, omega n in terms of V1, V2, Vn. So first we want to express somehow how those vectors are represented in terms of, like, the second basis is represented in terms of the first basis, right? And of course, they have some linear combinations that represent them. So those C11, C12, etc., they're just coefficients that represent this, omega 1 vector in terms of the old basis, V basis. Okay. Okay. So we find how omegas are expressed in terms of basis V. Good. Next is exactly the same step as before. So we know how omegas are expressed in terms of basis V. So instead of omega, we put the representations here. Instead of omega, we put their representations here, right? So you can see we just substitute the definition of what omega is in terms of basis V1, V2, Vn. And we open the brackets as before. And we find some relations between coefficients in front of V1 and what we know is the coordinates of A, so alpha 1. Some relations between coefficients in front of Vn. And what we know is coordinates of coordinate of A, so An. Okay. So we find this relation. And this tells us that A1, alpha 1, alpha 2, alpha n is related to gammas as this matrix multiplication. So, maybe I skipped a few steps here, but I think it is clear, right? You want to get this coefficient, you multiply those coordinates with gammas, right? And that is that comes from this relation. So gamma 1 C11 gamma 1, C11, gamma 2, C12, gamma 2, C12, gamma n, C1n, gamma n, C1n. That's alpha 1. You got it, right? So this is the, again, we got some matrix vector multiplication, which now tells us what alphas are in terms of gammas. Notice that if we want gammas, we have to invert this matrix now. This is not something you need to memorize. It just happens so. And the reason it happened so is because we expressed omegas in terms of basis v. If we did it otherwise, if we expressed v's in terms of basis omega, it could have been different. Yeah. I don't know if in algebra you studied those rules of how to transform one linear space into another linear space in terms of like basis vectors, etc. But basically, if you studied it and you found it difficult, I suggest always just do what I did here. Simply write it out and see how it turns out. Because it is easy to make a mistake, but when you write out like this, you would find correct answer. Like trying to reason through abstract entities is good when you understand them. If you don't, just write it out this way. All right, good. So what we found is that both operators can be expressed as what they do on coordinate in terms of coordinates, right? And then they become matrices. And change of basis can be expressed in terms of how coordinates change. And again, then change of basis becomes a matrix. Okay. So you notice that we have twice arrived at the vector matrix multiplication, but doing completely different things. Okay. Okay. So just let's note two things. In robotics, we sometimes talk about active rotations, as in when you rotate a vector and the result is expressed on the same basis as before. And then there are passive rotations. So that's just a change of basis. It can be difficult to understand, especially when active operations are performed like in a varying basis. So, you know, behind all of this difficulty lies what I just showed you in the previous slides. Either you're talking about operators or you talk about change of basis. But, you know, instead of trying to somehow find out if it is active or passive, just think about algebra. Don't, my suggestion, don't try to bring in this robotics jargon, active, passive rotations, etc. All of this is fluff. Like it helps if you understand what's going on, but algebra works fine. In algebra, people don't talk about active and, as far as I know, active and passive rotations. So, right. Okay, and they do fine. they manage. So now, our approach will not require this, right? So if you're going to use this active-passive combination in the future, you can try to verify it using like this type of thinking. All right, good. Now let us enter a how do you put it, like Wonderland, the Zerkalye. Now we're going to the most difficult part of this lecture. We're going to go to Rn. Before we were talking about abstract vectors, and there I could, as soon as you try to think about columns, I could stop you, say, no, this is not a column. This is a arrow or something. Right now, it will be difficult for me to stop you, but I still want you to think about abstract vectors, even in Rn, okay? So the risk of confusion is enormous. First, it is very difficult to find the difference between vectors and coordinates, right? What is the difference between vector in Rn and coordinates in Rn? Very difficult. You cannot tell by looking at a vector if it is a vector or coordinates. Second, a basis in Rn is just a matrix. And operator in Rn is also just a matrix. So you cannot tell the difference between a basis, a operator, and the matrices which implement those. They all look exactly the same. So confusion is very big. And when you studied linear algebra, I think the way you went around this confusion is you just assumed coordinates and vectors are the same thing. Operators and matrices are the same thing, which is true in many ways, and it works. But for us, we need to see the distinction. And believe me, it helps. It will help you when we do geometry. All right. So we will resist trying to mix them up. Okay. Now, assume that the columns of matrix V form orthonormal bases in V. Now we are starting to study orthonormal bases. That is extremely important. I don't know if you studied them well enough previously. So assume the columns of V form orthonormal bases in Rn. Orthonormal means all columns have norm 1, and they're all mutually orthogonal. Okay, so consider now vector A, which is alpha 1 v1 plus alpha 2 v2 plus alpha 3 v3, alpha n vn. We can find those coordinates now using dot product. We can find those coordinates as v1 dot a. Yeah, alpha 1 is equal v1 dot a. So now we finally have a way to compute coordinates. We don't have to just know them in advance. We can compute them. But we need to know A now. If we know A, we can compute alphas. How and why? Well, the reason this is true is because we have two properties. One is multiply any vector vi from this basis with itself, and it would give you 1. Multiply vi with any other vector from this basis, it will give you 0, right? So this is what you can use to prove this property. The way you can do it is you just write out this definition, right? Like let me show it. You get this definition. You multiply it by v1, for example. You multiply it by v1. You get 1 here and 0s everywhere else. 1 because of this property, 0s because of this property. So you have on the right-hand side, you get v1 times a, so this thing. On the left-hand side, you get alpha 1, which is this side. Okay? Do it with other vectors, you get the same thing. So that's how it works. Okay. Okay. If the basis is not orthonormal, we could still do the same thing, but it would be not as simple. I will leave it to you to think about it. Okay. Now we know how to find coordinates now in orthonormal spaces. So we can find all coordinates in one operation. We can just say alpha, so coordinates, are equal to a series of dot products, right? So dot product of v1 with a, v2 with a, v3 with a. By the way, here it should be, I'm missing here a transposition sign. This is a row vector. This should be a row vector. Yep. I think, no, yes? No, it shouldn't be. Sorry, it's not a row vector. Sorry, I was confused because of this. Sorry about that. Anyway, so we can represent those series of dot products this way, and what we get is just a multiplication of this basis matrix times a. So notice what we have is alpha. So coordinates are equal to just basis transposed times a. That's how you get coordinates. That is very important. If you don't remember it from linear algebra, please try to remember it now. This is extremely important. You have orthonormal basis. You want to find coordinates in this basis. Just multiply the vector by basis transposed. By basis, I mean, by matrix, I mean like matrix whose columns form a basis. And you get coordinates. That's how. Okay. So in general, if R is in Rn and B is a basis in and it is orthonormal basis, and P are coordinates, then on one hand, we can find R by multiplying B by P, and we can find P by multiplying R by B transposed. So let me one more time clarify. This is how you find vector when you know coordinates. This is how you find coordinates when you know vector. Please note, this is vector, this is coordinates, this is vector, those are coordinates. Okay. And B here is a basis, orthonormal basis. Okay, good. Good. Now, any matrix B whose columns form an orthonormal basis in Rn is called an orthonormal matrix. Those matrices have properties. For example, B inverse is equal to B transposed. You can try to prove this property yourself using definition of orthonormal basis that I gave you previous 2 slides. And B transposed equals times B is equal to 1. This you can prove using directly the previous property. Okay. Those are also just followed by definition. This is pretty much what I wrote 2 slides ago, but in my matrix form. And if you prove this, you can prove this again, elementary. Is there any questions about what is written here?
No.
Okay, good. Good. So now we have orthonormal. What we have in our tool belt is, we remember relations between vectors and coordinates in general. And we saw specifically how to find coordinates in orthonormal matrices. So those two are different things, remember. Bases don't have to be orthonormal, right? And all that we discussed in the beginning of the lecture was for just arbitrary bases. What we discuss now is for orthonormal bases. So don't confuse them. Okay. Now to practical finally. But I think it will be very very simple. So we got through the hard part. Now now the stuff that we usually study, and you will see how it's not very difficult now that we got through everything else. So let's consider a problem. So we have R expressed in orthogonal basis A. Okay. This basis is formed by columns of A, matrix A. Please notice I use bold to represent vectors and matrices. I use cursive to represent bases and other objects like this. So don't confuse a basis and a matrix that forms this basis. Okay. The reason not to confuse them is because matrix itself is represented in terms of some basis. Sorry, how should I put it? How should I put it? Let's think about it. So we have basis A, right? Those are just n vectors, like 3 vectors. Since we are talking about R3 now, it is just 3 vectors. Those 3 vectors, you can write them down, right, on a piece of paper as coordinates. And that is what A is. A is 3 vectors, but written as coordinates. But here's the kicker. Coordinates in terms of what? In terms of what? You understand? So, for example, you can write A in terms of coordinates of A. Then it would be identity. You can write A in terms of some other coordinates. Then it would be not identity. You understand? So basis and matrix are not identical. At least not here. Okay, good. So let us find, okay. Now, A subscript A is the coordinates of R in basis A. Okay. So R is an abstract vector. What I call abstract vector. So just a vector. These are coordinates in terms of A. Now, let us find coordinates of R in terms of a basis B formed by columns of B. Okay, let's do it. So as long as we know what R is, if we have knowledge of what R is somehow, then the solution is trivial. The solution is then absolutely requires no thought whatsoever. It is just that. If we know what R is, to find its coordinates in terms of basis B just means by definition to multiply it by B transposed. Please notice that is true. That is simply true. That is not somehow like somehow leap of concept or something, right? If we know what R is, we can always do this. All right, but R is abstract vector, so how would we know it? Of course we wouldn't. Okay. But we know what coordinates of R is in A, so that we can write it this way. R is equal to A times R subscript A. So now we know what R is. Now we know what R is. As long as A, we know what A is, and assume we do, then we have R. But we just said before, if we knew what R is, we could easily find what its coordinates in B are, just multiplied by B transposed. So we get the expression. We get the expression. It is that simple. Notice the task here sounded like a headache. Sounded like a headache. You have R expressed in basis A, formed by A, with coordinates. Let's find coordinates, etc. Right? Sounded like a headache. But using a very simple reasoning, we know how to find coordinates of any vector in terms of basis, right? So here, but we don't know R, we can find it. So substitute, you get expression. That is it. Try to make mistakes there. So apparently the transformation from coordinates in A to coordinates in B, in this case, is given by B transpose A. Do you want to memorize this fact? Do you want to try to memorize how to transform vector from expressed in terms of coordinates of the first basis to the coordinates in terms of the second basis? No, you don't. I hope you don't, because you would mix it up, right? You would just mix B and A, and you would get something else. Don't memorize it. Just use reasoning. Any question about this example? No questions, right? Okay. Now, let us just look at it for a second. So when you are going to write kinematics in robotics, you will feel like you always need to explain in which coordinates are like any vector lies. And here you have a vector which does not have coordinates, okay? Like this vector R is not expressed in terms of anything, okay? Like this vector R, it does not have a basis, does not have coordinates, is just a vector R. Trying to say that vector R is in terms of some kind of coordinates here leads to some sort of a rabbit hole. But of course, you may still want to say, well, you may say, okay, let us still kind of like define coordinates of R. Sure, you can say it is like world coordinates or something. Like you can call his basis as something. But if you do, be careful. Its basis, as far as I can tell, would be identity matrix here. So you can use that. But ultimately, what is going on here is that we use somehow, like instead of arguing about all vectors lying in some sort of coordinates, we argue about absolute knowledge about R. Like by definition of the problem, we knew coordinates of R in one of the bases. That was the solution. That was the key. And things like that happen. So they're actually prevalent. You always have some sort of a basis and some sort of coordinates in terms of this basis. So trying to put coordinates on R would only make it more difficult here. But my point here is to say, this is not how we usually reason. Why? Because people in robotics are not comfortable with having vectors without coordinates anywhere. And the reason is because it is easy to make a mistake if you, for example, omit these coordinates here. And remember, robotics is engineering science. So for your final reports or stuff like this, you cannot be sloppy. So you have to be very exact in your coordinate your transformations, etc. You have to provide all careful analysis. So if you, for example, work designing a robot for someone or for yourself, of course, provide coordinates whenever possible. But when you do quick computations, which is, in my experience, like 99% of the work, quick computations to understand something, then this works much better, I think. All right, let me give you another example. Do we have questions here?
No.
Okay. All right. Now example is maybe like horrifying. So we have R expressed in orthonormal basis A, formed by columns of A. We know that columns of A, we know columns of A as expressed in a different basis in C. And those columns in C are expressed as A subscript C. The basis C in terms is formed by columns of C, matrix C. We know that columns of matrix C are expressed in orthonormal basis omega and are given as omega C. Now, this already probably sounds like a nightmare, but that is typical forward robot kinematics. You have one basis expressed in terms of second basis, in terms of third basis. Okay. Now, you have another basis, orthonormal, of course, B, formed by columns of matrix B. And columns of this in this matrix B, we know it only as expressed in the basis omega. So all of this, the most basic basis here is omega. You can think about it as world frame. Now, the question is, find transformation T that maps coordinates of A as expressed in A, of R as expressed in A to coordinates of R as expressed in B. I hope, like if previous one was a headache, this I hope is a nightmare. I hope. I mean, I was just trying to motivate why we need to think about abstract vectors, why we cannot do this just head on, like run through the wall kind of thing. Okay, let me show you. Let me show you how it's solved. First, A is like we want to find how coordinates of R in terms of A are related to coordinates of R in terms of B. Let's go. So coordinates of R with respect to A are given as such. Just a definition. Okay. We don't know what A is, but we know what A sub C is. A sub C is columns of A expressed in terms of C. So that means that these are coordinates. Those are vectors. And we know how to get from coordinates to vectors. We multiply bases coordinates by the basis. So basis times coordinates gets original vector. Is it just that they are columns, so they're stacked horizontally, but changes nothing. So this is a familiar expression that we saw before, and this gives us transformation. Okay. So we have this way to transform coordinates into vectors. But we don't know what C is. Remember, we don't know what C is. We only know that C is expressed in omega as C sub omega. Okay. So C is given by coordinates C sub omega in terms of some basis omega. We don't know what omega is, of course, but we'll just leave it for now. So we know that C is equal to omega times C sub omega for the same reason as here. Those two are the same equation, just applied to different coordinate transformations. Okay, now let us substitute this here. What we get is this expression. Okay. Now we substitute this whole thing into here. And what we get is this expression. Now we open the transposition, and omega goes from here. Let me just show it. Omega goes from here to here. VC goes here. AC goes here. So we get omega transposed, C transposed, A transposed. So we get some somehow relations between R and A sub R. Okay. So far, so good. Next. Next, we do the same for B. This is by now familiar. Coordinates of B in terms of B will be equal to B transposed R. Okay. B transposed R. As before, we do not know B, but we know its coordinates. Okay. So we can find B in terms of its coordinates, right? Multiply coordinates by the basis, you get the vector. Now we substitute this here, and we get this expression. We open the brackets. Omega goes here. BW goes here. And we get the relations between coordinates of R in B and vector R. Okay, so now we have two such relations. One relation is this. Another relation is this. Okay. Now, what we can do is we can put this vector to the left-hand side and put this vector to the left-hand side. You understand how to do it, right? You multiply both sides by the inverse. But inverse is the same as transpose, because we are talking about orthonormal matrices. So we get this expression here. This is just A goes here, right? C omega goes here, and we get this expression downstairs. Here, B omega goes here. But note, they have the same right-hand side, so we can equate them. And here is what we get. C in terms of omega, A in terms of C, R in terms of A, B in terms of omega, R in terms of B. And from that, I think it is clear what's the next step. Next step is having this expression. We just express RB in terms of RA, and T transformation is this. The answer. That's it. Please notice, it was a lot of like 3 slides, but nothing there was difficult. We just applied the same coordinate vector in terms of coordinates, coordinates in terms of vector, vector in terms of coordinates, coordinates in terms of vector, again, again, again. And we did like extremely basic matrix multiplications, as in like matrix inversion, like how to put something from the left-hand side to the right-hand side. And that's it. That's it. That is all we did. Notice how simple it is for such a complicated problem. I mean, this problem just looks like a, I don't know, weekend, you know, can be spent. But you know, I don't know. Solution is not very difficult. Now I hope you understand the power of abstract vectors. You don't ask what omega is. You don't ask what R is. You just work with them. At the end, they are going to go away. Because all robotics questions are about coordinates. So at the end of the day, you're going to transform coordinates. But in between, you can use abstract vectors because questions are about coordinates, but objects are always real life arrows. So like, if I ask you, where are your camera points? Where are your camera points? I'm asking about an arrow. I'm not asking about 1, 3, 2.5. I'm asking about arrow. I'm asking about direction. So you have to give me direction. And in which frame you express this direction ultimately is a matter of choice. But you are perfectly, you know, in your right to work directly with this direction, not with coordinates of this direction. Okay, so that was what I wanted to teach you. But please remember, word of caution. Robotics is not a sprint. There is absolutely no advantage in trying to solve something very fast. Instead, solve something very carefully. My argument is that the method that I presented to you is careful enough, but verify, double check, think about what you do. Don't try to solve a problem in 5 minutes. If you solved something fast, verify. My personal philosophy is you solve something, then you find a problem that should, or example that should demonstrate that what you did is correct. Half the time it is animation. Half the time you can draw your robot and demonstrate that your forward kinematics agrees with what you see on the screen. Half the time you don't have animation, then you have to come up with artificial examples. Yeah. Yep. Also, again, my personal advice, write it down with intermediate derivations, as in just get like 10 pages and write everything, like all intermediate steps. Even if it is boring, don't worry. I understand like you're young, so for you boring things are not tolerable, but think about it as meditation, right? A lot of people go meditate, like clear their mind, etc. People find benefit in that. Consider derivations of formula as a form of meditation. I promise you that's not like complete craziness. You just need to focus on something. Is good. You spend half an hour doing the same thing 20 times instead of 5 minutes. Don't worry, half an hour is okay, and you will spend it being mindful. So it's not bad. I haven't seen any negative effects of on doing the same derivations again and again and again. I have seen benefits. I would suggest you try to do the same. At some point, you would understand that this derivation you can skip because you have done it so many times. You can do it without thinking. So at this point, you will know. But my suggestion: don't skip them until you have even tiny doubt. Okay, that was it for the lecture. Any questions? All right. I hope I didn't scare you away from the topic, or didn't bore you to death, or didn't make you skip your lunch because I probably took more time than we had. Right. Thank you, everyone. We'll see each other next week. And next week, we are going to go into core robotics, and we'll go into mechanisms. So, if you can, please don't skip next week. All right. See you. Bye-bye.
Thanks.
Bye-bye.